Hello. In today's lesson, we are going to discuss process scheduling algorithm. And by the end of this lesson, every student will be able to explain process scheduling algorithm, the meaning. Everyone will be able to explain objectives of process scheduling algorithms, and everyone will be able to perform fast come, fast served scheduling algorithm. Let's get started. So by definition, we define process scheduling algorithms as a set of procedures that are used by job scheduler to plan for the different processes to be assigned to the CPU. Remember, we defined the job scheduler as a program, an operating system program, which select from the pool of the processes which process is going to the CPU for execution. So the scheduler will check in the ready queue the list of the processes available, then decide which process goes next to the CPU for the execution. So the job scheduler uses a set of rules that we call algorithms to know which process has come first, which one is going to be executed first, which one is going to go next. So the algorithms are used to decide which next process is going to be executed. So by talking about objectives of process scheduling algorithms, so they are there to maximize the CPU utilization by keeping the CPU as busy as possible. So we have to know that the CPU should not stop working. So it has to work every single second, every single millisecond. It's like a brain. As we know, the CPU is a brain of the computer. What if the human brain stops working for 2 seconds? So the person goes inconscient. The same applies to computer. So the CPU has to be busy every time, every single millisecond. So the process scheduling will make sure the CPU has what to do always. It is fair allocation of the CPU to the process. So the scheduling algorithms will know which process has come first and which one has the high priority, which one has a low priority. There may be a list of processes, and in those processes there are some processes with high priority which need to execute before, even if they come last. So in that case, the CPU, the scheduling algorithm, will allow fair allocation of the CPU to the process. It maximizes the number of processes that complete their execution per time unit. So each process going to the CPU, the scheduler will know how long will it spend there. So it will now calculate and know the next process will come at this time. So all those are functionalities of the process scheduling algorithm. The process scheduling algorithm is there to minimize the time taken by the process to finish its execution. So the scheduler will try as possible to make sure every process does not spend long time in the execution. To minimize the time a process waits, in a ready queue. So imagine you have 10 processes all waiting to get executed. So the scheduler will make sure the processes are not spending a long time in the ready queue. To minimize the time it takes from when a request is submitted until the first response is announced. So the scheduler also will make sure the program is launched, is opened. So when you open a program, so now the scheduler will send a request to the program launcher to open a program from the hard disk, from the long-term scheduler, so that it is loaded into the memory, the main memory. So it will also have to calculate how long does it take to launch a program. So all those are activities of the scheduler, the program scheduler, or scheduling algorithms. So those are the main objectives, but you can find more other objectives of the process scheduling algorithms. So there exist 5 types of scheduling algorithms, and the programmer, the operating system developer will choose which type he or she is going to use with the operating system. But you may find that modern operating systems can have all those types of scheduling algorithms. So you're going to go through each and every type and see how it works. Before we begin, let's talk about something here. All the above 5 types can either use non-preemptive or preemptive methods. What that means? In non-preemptive algorithms, the process which has entered in the learning state, it cannot be preempted, it cannot be interrupted until it completes its allocated time. Let's take an example of process P1, which is already in execution mode. And the scheduler has decided that process will spend there 10 seconds. So no any other process, whether it has a high priority or any kind of process, will interrupt that process which is already in execution until it completes. So we call that non-preemptive algorithm. Then in preemptive scheduling, the scheduler may preempt, may interrupt a low priority running process anytime when a high priority process enters in a ready queue or in a ready state, which means there is a process P1 being executed. It has to spend there 10 seconds. It has used, let's say, 3 seconds. There comes a process with high priority. So that one with a high priority will go in execution. Then the P0, which have spent 3 seconds, will be interrupted, will be put on the ready queue. Then when the high priority process completes, the one interrupted will go and finishes its time remaining, means 7 seconds. So in that case, the scheduler being used is preemptive scheduling algorithm. So those are two possible methods that can be used when scheduling algorithms are being defined. Let's discuss the first come, the first served scheduling algorithm. So this algorithm has a basic principle to allocate a process to a CPU in their order of arrival. Let's say we have 5 processes, A, B, C, D, E. So in the first come, first served, the process will be allocated to the CPU in order of their arrival, which means the one comes first will be executed first. So first come, first served is a non-preemptive scheduling algorithm, which means the process assigned to the CPU will have to complete its time allocated so that the second or the next process take place. This algorithm is managed with a first in, a first out. It is non-preemptive because the CPU has been allocated to a process that keeps it busy until it is released. So which means if the CPU is busy working on a process, no other process can interrupt the one in execution. When a process enters the ready queue, a process control block or PCB is linked onto the tail of the queue. So which means whenever you launch a program and a new job is created, so it will goes on the tail of the queue. When the CPU is done executing a process and is free, the job scheduler selects from the head of the queue the next process to get into the CPU. And this has a very negative impact, which will result in a poor utilization of the resources in the computer, since it cannot utilize the resources in parallel, which means if the process has occupied a given resource, let's say it's a camera, and there is another CPU process which will need the camera, so that one cannot be allocated to that resource until the first one releases that resource. Let's say you are calling using Skype, and also you want to scan, you want a QR scan. So in that case, we have two processes, scanning a code, and the camera is busy with the Skype. So the scanning will not take place until you leave Skype. So in that case, the management of resources will be a problem. So, and that will result in blocking. Processes may block each other, and that may lead to the system crash. So before seeing how to perform first come, first served, let's understand the key terms that we use when calculating the time allocated for each processes. The first term is what we call CPU burst time, or BT. So this is the time required to complete a process execution in the CPU. For example, we have a process P1, which has to execute for 10 seconds. So in that case, 10 seconds is the burst time for P1. Then each process has to mark the alive time. The alive time, this is the time at which the process arrives in the ready queue. Every time the process enters the ready queue, the scheduler will mark the time it has arrived. We have what we call Gantt chart, which is an horizontal bar which illustrates the list of available processes and their required time to execute. We have completion time, CT. This is the time at which a process completes its execution. We have turnaround time, TAT. This is the total time between submission of the process and its completion. The time between the time the process has started the execution and the time it has ended, so that interval we call it turnaround time. And to calculate turnaround time, we use the formula by taking the completion time, then we subtract arrival time, and from there we get the turnaround time. We also have wait time, which is the time a process spends in the ready queue waiting to execute. To calculate that, we use the formula turnaround subtract or negative burst time, which is the total time a process should use in the execution. So those are the terms we'll be using in all the types of scheduling while doing some calculations. Now, let's start by seeing how to calculate, how to perform first come, first served. Let's take an example of 3 processes: process A, process B, process C, and their burst time and their arrival time. So these processes have come at the same time at 0 millisecond. And the instruction here say that they arrived in the order of A, B, C. So which means even if they arrived at the same time, there is no way a scheduler can schedule all the same at the same time in the CPU. So it needs to decide this goes first, this goes next, this goes next. So the order is ABC. The instruction may come saying the order is CBA or CAB, but the order here is ABC. So which means the process A to complete will use 24 milliseconds. Process B will use 3 milliseconds. Process C will use 3 milliseconds. Now, the first step, you have to draw the Gantt chart by showing all the processes. You show when each process is going to finish and when it has arrived. Here we can see now the process number 1, which is A, has arrived at 0 milliseconds, as well as B and C. Now, at 0 milliseconds, the process A started, and it's going to use 24 milliseconds, which means at 24 milliseconds, when it completes, process B will begin. And process B will spend 3 milliseconds in the execution, which means the process B will complete at 27 milliseconds. Then when it completes at 27, then process C will begin, and process C will spend there 3 milliseconds, and it will complete at 30 milliseconds. That is the first step. You have to draw Gantt chart showing when each and every process is going to complete. Step number 2, after having your Gantt chart, now you can calculate turnaround time, TAT, by taking completion time, then you subtract arrival time, which means process A will complete at 24. If we subtract arrival time, which is 0, so the turnaround will be 24. The process B will complete at 27. If we subtract 0, which is the arrival time, we'll find that TAT for B is 27. Then process C will complete at 30 milliseconds. Then if we subtract 0, we'll find that TAT is 30. Then after having your TAT, now you can calculate average turnaround time by taking TAT for each process. You calculate, you sum up them, then you divide the number of processes, and we'll find that the average TAT is 27 milliseconds. After getting the TAT, now you can calculate the waiting time, how long each process has spent in the ready queue. So to do that, we take turnaround time, then we subtract burst time. Now, TAT for process A is 24. Then if we subtract burst time, which is 24, we'll find that the wait time for process A is 0. So the process A has spent 0 milliseconds waiting. Then process B has spent how long? So we take 27, which is not 27. We take 27, which is a TAT here. Then we subtract the burst time, which is 3. Now it's 27 negative 3, and we get 24. So 24 is the wait time for process B, which means process B has spent 24 milliseconds waiting to execute. Then for process C, we have 30, which is TAT. Then the burst time for process C is 3. Then find that the process C also has spent 27 milliseconds waiting its execution. So now we can calculate average wait time. Then we find that the process A will wait for 0 milliseconds, B will wait 24, 3 will wait 27, then we divide by 3, and we'll find that the average wait time is 17 milliseconds. So each process on average has spent 17 milliseconds waiting the execution. So this is how to perform the first come, first served when the arrival time is the same. So what will happen if the arrival time is not the same? Let's take an example number 2. So the example number 2, in example number 2, we have 5 processes: P0, P1, P2, P3, and P4, and their arrived time. So we found that the P0 arrived at 0 millisecond, P1 at 1, P2 at 2, P3 at 3, P4 at 4, P5 at 4. And we have their burst time. So we find that we have the process P0, which is going to use 2 milliseconds. Process number 1, P1, is going to use 6 milliseconds. Process 3 is going to use 4. Process number 4, 9. Process number 5 is going to use 12 milliseconds. So now, first step, as we said, we have to draw Gantt chart. So we have process 0, P2, P1, P2, P3, and P4. So the process 1 came at 0, and it's going to use 2 milliseconds, and it is going to complete at 2 milliseconds. Process 1 is going to use 6 milliseconds to complete, so which means it will complete at 8. Then process 2, P2, requires 4 milliseconds to complete, so it will complete at 12. Process P3 requires 9, so it will complete at 21, while P4, which requires 12 milliseconds, is going to complete at 33. So now we are going to, we have our Gantt chart. Now we can use that to calculate. So the completion time is here. This is the completion time as it is shown on the Gantt chart. So now we are going to calculate turnaround time. And as we said, the turnaround time is completion. So the turnaround time is the completion time minus arrival time. So which means the turnaround for process P0 will be 2 negative 0, because they arrived at 0. Then here you have 8, which is a completion time, then it arrived at 1. Here we have 12, which is a completion time, and it arrived at 2. Then here we have 21. Then we subtract 4, 3, Then here we have 20, 33, we subtract 4. So now this is our turnaround time, and you can calculate average turnaround time, and you will find that each process completion interval will be 13.2 milliseconds. Then after having our turnaround time, we can calculate wait time. The wait time, remember the wait time is in the turnaround minus burst time. So this will be 2, and 2 requires 2 milliseconds. Then we have 0. Then here we have 7. Then we subtract 6. Here we have 10. Then we subtract 4. Then here we have 18. Then we subtract 9. Then here it's 29 minus 12. So then we have our wait time, and you can calculate average wait time, and we found that each process will wait at least 6.6 milliseconds. So this is how to perform. First come, first served when the time is the same or when the time is different. So, may you have any question? So you can feel free to send me an email. And here we have assignment, 2 questions that you are going to try. We have 4 processes, and their arrival time and their burst time. Question number 2, we have 5 processes which came at the same time, 0. Then we are going to go through calculations and calculate average wait time and average turnaround time. So this is the end of the lesson. Then thank you.